The workshop in Copenhagen carried the particular smell of machine oil and brass shavings that defined precision manufacturing in 1900. Vilhelm Olaf Madsen stood before a disassembled prototype on the workbench, its mechanical components spread across oil-stained paper like the organs of some industrial creature awaiting resurrection. He was not, strictly speaking, a hardware designer. His official position was Minister of Defense for Denmark, a political appointment that should have kept him in meeting rooms discussing budgets and procurement contracts. Instead, he spent his evenings here, in this converted carriage house behind the Danske Rekkelriffel Syndikat factory, collaborating with two men whose expertise complemented his vision. Julius Rasmussen adjusted his wireframe spectacles and examined the pivoting breech block, the heart of their controversial design. Beside him, Theodor Skaubo sketched modifications to the magazine feed system, his pencil moving with the practiced precision of someone who thought in three-dimensional mechanical relationships. The three men had been working together for 4 years, ever since Madsen had secured funding from the Danish government to develop a lighter alternative to the Maxim systems that dominated military inventories across Europe. The challenge before them was unprecedented. Every successful automatic system in service operated on principles established by Hiram Maxim in the 1880s, heavy, water-cooled, crew-served equipment that required fixed positions and substantial logistical support. The toggle lock action Maxim had perfected was elegant in its way, but it demanded precise manufacturing tolerances and substantial mass to manage physical forces. Attempts to lighten these tools had universally failed, producing either unreliable actions or operational forces that made accurate use impossible. Madsen's approach rejected the assumption that simplicity equaled reliability. His design featured a breech block mounted on a lateral hinge that would swing through a complex arc during each cycle. When Rasmussen first saw the drawings, he'd called it mechanically excessive, counting over 100 individual parts that would need to function in precise coordination. But Madsen had argued that distributing the mechanical stress across multiple components, rather than concentrating it in a few heavy parts, might actually increase reliability while reducing overall weight. The barrel assembly sat in a machined housing that allowed it to move backward against spring pressure. The breech block, positioned above and to the rear, would swing downward and forward as the barrel returned to its starting position, stripping a cartridge from the overhead magazine and chambering it. Upon activation, barrel and breech block would move together approximately 12 millimeters before a cam surface would unlock the block, allowing it to pivot downward and extract the spent case. The cycle would repeat as long as the trigger remained engaged and ammunition fed from the magazine. Skaubo had insisted on the overhead magazine placement despite criticism from technical observers. Bottom-mounted magazines made more intuitive sense, following the design of existing equipment, but they created feeding problems when the device was used from low-profile positions. The curved overhead magazine, gravity-assisted and positioned where it wouldn't interfere with sight lines or ground clearance, seemed awkward until one considered the actual conditions under which personnel would employ the device. The current prototype weighed 19 pounds without ammunition, less than half the weight of a Maxim system, yet still substantial enough to stabilize during rapid operation. They had tested it 3 days earlier at the government proving ground outside Copenhagen, and the results had been simultaneously encouraging and concerning. The device had functioned 300 times without malfunction, demonstrating mechanical reliability that surprised even Madsen. But the complexity of the action made field maintenance a concern, and the curved magazine required specialized manufacturing that would increase production costs significantly. Madsen lifted the breech block assembly, feeling its weight in his hands. The heat treating on the steel was perfect, the machining tolerances exact. Whether it would prove practical in operational conditions remained uncertain. But standing in that workshop, surrounded by the tools and materials of precision engineering, he felt confident they had created something fundamentally new, a tool that moved with the user rather than anchoring them to fixed positions. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. The pressure came from multiple directions simultaneously, as it always did when innovation threatened established patterns. Denmark's procurement committee had reviewed the Madsen design and expressed polite skepticism. Senior officers, trained in tactics that assumed heavy systems would operate from prepared positions with interlocking fields of coverage, questioned whether mobile units needed portable automatic tools at all. Several committee members advocated purchasing additional Maxim systems from established manufacturers rather than investing in an unproven domestic design. International manufacturers sensed the potential threat. Representatives from Deutsche Waffen und Munitionsfabriken visited Copenhagen, offering licensing agreements for their own light equipment developments. The Maxim company's agents suggested that Denmark's limited industrial capacity made domestic production economically impractical. These weren't merely commercial negotiations. They carried implicit warnings about diplomatic complications if Denmark's design proved successful enough to threaten established market positions. Madsen's political position created its own complications. As Minister of Defense, any decision to adopt the equipment he'd helped design would invite accusations of conflict of interest and self-dealing. Opposition politicians prepared questions for Parliament about government funding flowing to a project in which the minister held financial stakes. The Danish press, typically supportive of modernization, began publishing articles questioning whether taxpayer money was funding a politician's mechanical hobby. Rasmussen handled the technical challenges with methodical precision. Each test session revealed small issues, a feed ramp angle that caused occasional jams, spring tensions that needed adjustment, heat dissipation concerns after sustained use. He maintained detailed logs, documenting every malfunction and modification, building an empirical record that demonstrated systematic improvement. The machining requirements were demanding, but Rasmussen argued this actually increased reliability. Precision manufacturing meant tighter tolerances and more consistent performance. Skubo focused on ammunition compatibility, a crucial concern that received less attention than it deserved. European organizations were transitioning from black powder to smokeless powder cartridges, but this transition was proceeding unevenly across different nations. The Madsen design needed to function reliably with varying powder charges, projectile weights, and case dimensions. Skubo conducted extensive testing with ammunition from multiple manufacturers, documenting how the recoil-operated action adapted to different chamber pressures without requiring manual adjustment. The overhead magazine remained controversial. Technical observers found its appearance ungainly, and some suggested it would catch on vegetation or create balance problems during rapid movement. Skubo responded by organizing field trials where personnel carried loaded prototypes across varied terrain, demonstrating that the magazine's placement actually improved handling compared to equipment with bottom-mounted magazines that interfered with low-profile positions. Financial pressure mounted as development costs exceeded initial projections. The complex machining required specialized equipment and skilled workers, both of which commanded premium wages. Madsen secured additional government funding by arguing that developing domestic manufacturing capability had strategic value beyond the immediate design. If Denmark could produce precision mechanisms domestically, it reduced dependence on foreign suppliers during potential international tensions. By early 1902, Madsen faced a critical decision. The device functioned reliably in controlled testing, but formal adoption would require extensive field trials that could reveal problems after significant resources had been committed. Conservative doctrine suggested purchasing proven foreign designs, avoiding the risk and expense of unproven innovation. Yet every field report from distant conflicts reinforced the same conclusion. Modern engagement was moving toward mobility and dispersed formations where traditional heavy equipment couldn't provide adequate support. Madsen authorized final preparations for formal evaluation, knowing that success or failure would define not just the project's future, but his own political career and Denmark's position in the evolving international market. The mechanism worked. Whether it could survive the institutional resistance to genuine innovation remained uncertain. The mechanism's logic emerged from a fundamental insight about energy management. Traditional designs attempted to contain physical forces through mass and mechanical bracing, creating equipment too heavy for individual users to operate effectively. Madsen's approach instead distributed those forces across multiple moving parts, each absorbing a fraction of the total energy. The result was counterintuitive. More moving parts created smoother operation and less felt impact than supposedly simpler designs. The cycle began with the barrel and breech block locked together in the starting position. The breech block sat at the upper rear of the action, tilted backward at approximately 30 degrees from vertical. When the trigger released the mechanism, the pin struck the cartridge primer while the block remained securely locked against the barrel extension. The initial impulse drove both components rearward as a unit, maintaining the locked condition during peak chamber pressure when mechanism failure would be critical. After 12 millimeters of travel, a cam surface on the receiver engaged a roller on the breech block's lower edge. This cam forced the block to rotate downward on its lateral pivot pin while the barrel continued its rearward movement. The unlocking occurred after chamber pressure had dropped to safe levels, but while sufficient residual pressure remained to drive the extraction process. The spent cartridge case moved with the rotating block until it contacted a fixed ejector that kicked it clear of the action through a port on the right side. As the breech block completed its downward rotation, it moved forward and downward toward the magazine feed position. The barrel, meanwhile, had reached the limit of its rearward travel and compressed the return spring fully. The spring's energy drove the barrel forward while the breech block continued its arc toward the magazine. Timing was critical here. The block needed to position itself below the magazine's feed lips precisely as the next cartridge became available. The magazine itself embodied elegant problem-solving. Curved to match the taper of the rimmed 8mm cartridges Denmark had adopted, it held 25 rounds in a spring-loaded stack. Gravity and spring pressure combined to present cartridges to the breech block's feed face. The block's forward-upward rotation stripped the next round from the magazine and pushed it into the chamber as the barrel completed its forward movement. The locking surfaces engaged automatically as the block rotated upward to its active position, ready for the next cycle. The entire sequence, unlock, extract, eject, feed, chamber, lock, occurred in approximately 1/20th of a second during sustained operation. Each mechanical event was timed by the precise geometry of cams, pivot points, and spring pressures rather than relying on external power sources. The device cycled at roughly 450 rounds per minute, a rate determined not by arbitrary limits, but by the speed at which each component could complete its motion reliably. Rasmussen had calculated the forces acting on each component during the cycle, ensuring that no single part experienced stress levels approaching its material limits. The breech block's pivoting motion converted linear energy into rotational movement, reducing peak forces. The barrel's limited travel meant lower internal velocity and gentler extraction. The distributed spring system meant gradual energy absorption rather than shock loading. The feed mechanism required particular precision. The magazine's curved geometry meant each cartridge sat at a slightly different angle relative to the feed lips. Scubo had designed the feed lips with compound curves that guided cartridges into alignment regardless of their position in the stack. The breech block's stripper face had corresponding angles that compensated for minor misalignments, maintaining reliable feeding. Cooling was passive but effective. The barrel's limited movement meant it remained relatively stationary, allowing air circulation around the exterior. The action's complexity meant more surface area for heat dissipation compared to simpler designs with fewer, larger components. Sustained tests demonstrated that the Madsen could operate for 200 rounds continuously without degradation in function, adequate for support roles where use would naturally occur in shorter bursts. The mechanical logic was complete, proven through mathematical analysis and empirical testing. Each component's function derived necessarily from the design constraints and desired performance. Yet translating mechanical logic into field reliability would require validation under conditions no laboratory could replicate. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. Field trials began in March 1902 at the Herrens Materielgård Proving Ground, where Denmark tested equipment under conditions approximating operational use. The evaluation committee included experts from multiple branches and external observers from allied nations who maintained Denmark's traditional neutrality. Their mandate was comprehensive: assess reliability, maintainability, durability, and tactical utility across scenarios ranging from defensive positions to advancing support. The first week focused on baseline performance metrics. Operating from fixed positions with trained personnel, the Madsen prototypes performed consistently well. Accuracy at 300 meters proved adequate for area coverage, though the device wasn't intended for precision tasks. Ammunition consumption tests confirmed that the 25-round magazine provided approximately 3 seconds of continuous use, requiring frequent reloading but allowing better discipline than belt-fed systems. Maintenance procedures revealed the design's most significant challenge. Complete disassembly for cleaning required removing the breech block assembly, which involved pulling the lateral pivot pin and carefully extracting the block and its attached components. Reassembly demanded attention to proper orientation and component sequencing. Several junior personnel struggled initially, leading evaluators to question whether field maintenance under high-stress conditions would be practical. Rasmussen responded by creating simplified protocols, focusing on the most common maintenance points, leaving complete disassembly for specialist-level care. Environmental testing introduced controlled variables. The equipment was deliberately exposed to sand, mud, rain, and temperature extremes, then used without cleaning. Results were mixed. The mechanism's complexity meant more surfaces where contamination could interfere with function, but the distributed design meant that partial contamination rarely caused complete failure. A heavily fouled Madsen might experience occasional feeding problems, but it rarely stopped functioning completely. Simpler designs, by contrast, tended to either work perfectly or fail catastrophically. The overhead magazine's performance exceeded expectations in some respects while revealing limitations in others. Personnel using it from low-profile positions appreciated that the magazine didn't interfere with ground clearance. However, reloading while in those positions proved awkward, requiring the operator to adjust their stance to access the magazine well. The curved magazine geometry, while functionally sound, required specialized manufacturing that would complicate logistics if other nations adopted the system. Sustained use tests pushed the equipment toward its thermal and mechanical limits. After a high volume of use in a short period, representing intense defensive support, the barrel showed significant heat discoloration, and the action's tolerances had loosened noticeably from thermal expansion. Allowing the device to cool for 30 minutes restored normal function, suggesting that burst operation with brief pauses, the typical usage pattern, would avoid thermal issues. Durability testing involved deliberate rough handling. Equipment was dropped from heights approximating operational scenarios and subjected to repeated impacts. The complex mechanism proved surprisingly resilient. While individual components occasionally bent or broke under extreme stress, the distributed design meant that damage to one part rarely rendered the entire tool inoperable. Field repairs proved feasible, though they required trained personnel and spare parts. Comparative testing against contemporary equipment provided context. A Maxim system delivered superior sustained performance and greater long-range accuracy, but required a 3-person team and weighed over 5 times as much as the Madsen. Existing automatic tools from other manufacturers showed either reliability problems or excessive weight. The Madsen occupied a unique niche, heavy enough to provide stable operation, light enough for individual use, reliable enough for field conditions. The Evaluation Committee's preliminary report acknowledged technical achievement while expressing reservations about practical implementation. The device functioned as designed, demonstrated adequate reliability under varied conditions, and offered tactical capabilities that existing equipment couldn't match. However, the manufacturing complexity would limit production capacity, and the maintenance requirements exceeded those of standard equipment. Madsen received the report with mixed feelings. Technical validation satisfied the engineering requirements, but institutional acceptance remained uncertain. The tool's future would be determined not by its mechanical performance, but by whether doctrine could adapt to incorporate capabilities that existing frameworks didn't anticipate. The final curiosity that would define the Madsen's legacy was discovered not during initial development, but gradually over decades of use across diverse environments and conflicts. By 1910, more than 30 nations had purchased Madsen systems, from major powers like Russia to others like Brazil and Mexico. Each adopted the tool for different reasons and employed it under conditions the Danish developers had never anticipated. The pattern that emerged was both unexpected and revealing. The complex mechanism that critics had predicted would cause maintenance problems in field conditions actually demonstrated superior adaptability compared to theoretically simpler designs. The distributed stress architecture meant that normal wear affected each component gradually, rather than concentrating on a few critical parts. A well-maintained Madsen could function tens of thousands of times before requiring significant component replacement, while supposedly simpler tools often experienced catastrophic failures of primary components that rendered them completely inoperable. Temperature extremes revealed the design's counterintuitive advantage. In tropical environments where heat and humidity caused metal fatigue and corrosion, the Madsen's multiple small components could be individually inspected and replaced without discarding the entire action. In Arctic conditions where lubricants thickened and metal became brittle, the mechanism's distributed forces meant that no single component experienced stress levels that would cause cold weather failures. Competing designs optimized for specific conditions often failed completely when deployed outside their intended environment. Ammunition quality presented the most significant real-world challenge. Standard cartridges produced under strict quality control worked reliably in most designs, but field conditions often meant ammunition manufactured to varying standards, stored improperly, or produced by multiple contractors with inconsistent specifications. The Madsen's recoil-operated action proved remarkably tolerant of these variations. Internal pressure fluctuations that would have caused timing problems in gas-operated systems were absorbed by the mechanism's inherent flexibility. The overhead magazine, controversial during initial evaluation, demonstrated unexpected utility. While bottom-mounted magazines made more intuitive sense, they created problems in restricted spaces and dense vegetation where ground clearance was limited. The Madsen's magazine placement meant it could be operated effectively from positions where other systems experienced feeding problems. Additionally, the magazine's removal for tactical reloading proved faster and more intuitive under stress than belt-fed systems that required careful loading procedures. Manufacturing complexity, initially viewed as a liability, became an unexpected advantage as global industrial capacity expanded. The mechanism required precise machining, but this precision was distributed across many relatively simple components rather than concentrated in a few extremely demanding parts. Small workshops with basic equipment could produce replacement parts, while competing designs often required specialized manufacturing facilities. This decentralized production capability meant that nations without advanced industrial infrastructure could maintain and repair Madsen systems domestically. The design's longevity provided the ultimate validation. Systems adopted in 1902 remained in service through the first half of the century, where they proved effective in conditions ranging from alpine mountains to desert environments. Interwar modifications addressed minor issues without changing the fundamental mechanism. During subsequent decades, Madsen systems manufactured in the 1910s functioned alongside equipment produced 30 years later, demonstrating mechanical longevity that supposedly superior designs couldn't match. The final curiosity was simple but profound. A tool designed using 19th-century engineering principles remained relevant into the second half of the 20th century. While competitors simplified their designs with each generation, eliminating parts to reduce production costs, the Madsen's elaborate mechanism proved more fundamentally sound. Complexity, when properly organized and distributed, created robustness rather than fragility. The tool's 70-year service life wasn't despite its mechanical complexity, but because that complexity was structured in ways that distributed stress and facilitated maintenance across diverse conditions. The Madsen's production finally ceased in 1955, though systems manufactured decades earlier continued seeing service into the 1970s in various regional contexts. Over half a century of continuous production had resulted in approximately 40,000 units delivered to customers across 6 continents. The design that committees had questioned for being too complex had outlasted supposedly superior equipment by multiple generations. The legacy extended beyond the tool itself into manufacturing philosophy and design methodology. The Madsen demonstrated that mechanical elegance didn't necessarily mean simplicity, but rather the intelligent organization of complexity. This principle influenced subsequent development, though not always explicitly. Designers began considering not just component count, but stress distribution, maintenance accessibility, and adaptability to varying conditions. The assumption that fewer parts automatically meant greater reliability was permanently challenged. Educational institutions studying mechanical engineering incorporated Madsen mechanisms into curriculum materials. The recoil-operated action with pivoting breech block became a standard example of creative problem-solving within severe constraints. The tool illustrated how seemingly contradictory requirements, lightweight, sustained capability, reliability, manufacturability, could be reconciled through sophisticated rather than simplified design. Engineering students analyzed the cam geometries, spring calculations, and timing sequences, learning that elegant solutions sometimes required embracing rather than avoiding complexity. The manufacturing legacy persisted in Scandinavia's precision engineering industry. Companies that had produced Madsen components developed expertise in tight-tolerance machining, complex assembly procedures, and quality control systems. This capability transferred to other industries, including automotive components, precision instruments, and eventually aerospace applications. The discipline required to manufacture a 100-component mechanism that would function reliably under extreme conditions proved valuable far beyond its original application. Operational doctrine evolved to accommodate the capabilities that tools like the Madsen had demonstrated. The concept of small teams centered around portable automatic systems became universal by the 1930s, transforming tactical thinking about maneuver and support. While other designs eventually superseded the Madsen in most inventories, the capability requirements it had validated, individual operation, sustained capability, and mobility, became baseline expectations for such equipment. The nations that adopted the Madsen earliest gained advantages that extended beyond pure functional performance. Operating and maintaining the tool required technical training that elevated general mechanical literacy among their personnel. Those who understood the Madsen's mechanism developed troubleshooting capabilities and mechanical intuition that proved valuable across various types of equipment. This unintended educational benefit contributed to broader technological modernization in several countries that lacked extensive industrial infrastructure. The final production runs in the 1950s incorporated minor modifications based on 50 years of field experience, but the fundamental mechanism remained unchanged from the 1902 design. This consistency across half a century of production demonstrated that the original engineering decisions had been fundamentally sound. While other equipment went through multiple generations of revision, each attempting to address problems revealed by use, the Madsen's core design required only incremental refinement. The tool's ultimate significance lies not in production numbers, but in what it proved about engineering methodology. Vilhelm Madsen, Julius Rasmussen, and Theodor Schober had created something that contradicted prevailing assumptions about mechanical design. Their willingness to embrace complexity when that complexity solved real problems, their distribution of mechanical stress across multiple components, and their attention to adaptability across varying conditions produced a design that remained relevant far longer than contemporary alternatives. Standing in Copenhagen today, one can visit the Tøjhus Museet Museum, where early Madsen prototypes rest in climate-controlled displays. The mechanisms, over a century old, still show the precision machining and thoughtful design that characterized their creation. They represent a particular moment in engineering history when creative thinking about mechanical problems produced solutions that transcended their immediate context, offering lessons that remain relevant as new technologies create new constraints requiring similarly innovative responses. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.